Hi guys, in this video we're going to talk about the work-energy theorem. By definition, the work done by a net force on an object is equal to the change in the kinetic energy of the object. By means of a formula, W net is equal to delta EK. Suppose we have a truck, that is being accelerated from an initial velocity vi by a net force F net that acts in the eastern direction. So the truck is accelerated eastwards by this net force, and acceleration means there is a change in velocity from a velocity value of vi to a velocity value of vf. Since the velocity values change, then we can already see that there's going to be a change in the kinetic energy of the object. Where does the work-energy theorem come about, or how does it come about? Well, if we start with the formula Vf squared equals Vi squared plus 2a delta x, or in some cases you might, using different symbols, you might want to use V squared equals U squared plus 2ax, same formula. Subtracting Vi squared from both sides, divide both sides by 2, multiplying both sides by m, we result with half mvf squared minus half mvi squared is equal to ma delta x. This becomes delta ek is equal to f net delta x. So delta ek simply means the final kinetic energy minus the initial kinetic energy. Rearranging that, we end up with W net equals delta EK, where W net represents the work done by the net force. Now, the important skill here is just to have three ways of looking at the net work done on an object by a system of forces. Which of the ways you'll adopt in the question will now depend on the information given. So, getting information out of the question becomes an important skill. Method 1 is the work approach. In this approach, we say W net is equal to the work done by force 1, work done by force 2, the work done by force 3, the work done by force 4. Well, it depends on the scenario, how many forces you have at play. So here you'd want to draw a free body diagram so that you can clearly see the forces. Be aware of negative and positive work. In the previous video, we've talked about what positive work and what negative work is. In this approach, you're basically saying, again, from my free body diagram, I can see the forces. I can calculate the net force as a vector sum of all the forces that are acting on the object. Once I get the net force, now I can say W net, the work done, or the total work done, is equal to F net delta x times cos of theta. Again, you need to take cognizance of the fact that some forces are positive and others are negative, and other forces have no components in the direction of motion. The normal force and the gravitational force, for example, when the object acts, when an object moves along an horizontal surface, the normal force and the gravitational force will have no components in the direction of motion. The other approach is to say, well, the change in kinetic energy. If you see a question giving you two different speed values or two velocity values, then most likely you can calculate the kinetic energy of the object, the change in kinetic energy of the object, and therefore once you get the change in kinetic energy of the object, you can equate that to the net work done on the object. So in summary, you're basically saying W net is equal to delta EK is equal to F net delta x is equal to work done by force 1 by force 2, depending on how many forces you have. As to which of this formula you're going to use will depend on the information given. So it is important to be able to read the question carefully and sift out the information. Okay, so much about the theories behind the work-energy theorem, guys. Now it's practice time. Don't disappear yet. Stick around. Let's do some practice on the work-energy theorem. In the first question, we're told a bullet of mass 50 grams is fired into a block of mass 4,950 grams. After striking the block, the bullet becomes embedded in the block, and the bullet block system travels a distance of 1,5 meters before coming to stop. The frictional force that acts on the block is 15 newtons. Okay. 1.1, we're asked to state the work-energy theorem in words. Well, we've already said the work-energy theorem states that the work done by the net force is equal to the change in the kinetic energy. Okay, so let's move now to 1.2. Use the work-energy theorem. And guys, we're emphasizing this idea that whenever you're calculating work, it's always helpful to come up with a free body diagram. Now, as we can see, this is a horizontal movement system, so the only forces that are of interest will be the horizontal forces. Okay, we've already discussed the fact that vertical forces will do no work. So we are told of a frictional force that acts on this object. Is there any other force that we can think of, that we can see? No. I know a lot of learners fall into the trap of always wanting to put in applied force. But guys, not every free body diagram will have an applied force. Sometimes an object keeps moving because it has momentum, not because it's being pushed. In this case, the frictional force is the only force acting horizontally. So which means the frictional force also becomes the net force. Okay, so from what we know, we say that friction always acts at 180 degrees to the direction of motion. So the object is moving east, the friction is at 180 degrees. Okay, it would be useful now to work out the work done by friction, because now we know that the frictional force is the only force acting. Okay, so what will be the work done by the friction? It's going to be the frictional force 15 times 1,5 times the cos of 180 degrees. Okay, this will give you a negative 22,5 joules. Okay, now 1.2 says we need to use the work-energy theorem, so we have to make an opening statement. It says W net is equal to delta EK. W net, the net work done. We know that the net work done is the work done by all the forces that are acting on the object. The normal force and the gravitational force will do zero work, so we'll be left with only the work done by friction. Delta EK is the change in kinetic energy. The object comes to a stop, so we know that VF is 0, but the VI, we won't know what it is. And that is what we want to calculate, the initial velocity. So, negative 22,5 is now equal to the final kinetic energy will be 0. Okay? We know that kinetic energy is half mv squared. So the initial kinetic energy will be half mvi squared. This is a half times. Now the mass of the block and bullet system, we're going to have to add them together. We're going to add the 50 grams and the 4,950 grams. That becomes 5,000 grams, which is 5 kg. Okay, so back to the calculation. So it's half times 5 times vi squared. Half times 5 is now 2,5. Okay, since we now know that this final kinetic energy is 0, so it's half 0 minus 2,5 vi squared. So the right hand becomes negative 2,5. Okay, so it was 0, can remove that, becomes negative 2,5. The next thing is to divide both sides by negative 2,5. You end up with vi squared equals 9. Therefore vi must be the square root of 9. Take square root of both sides. It's going to be 3 meters per second. It's a velocity value. We want a velocity value east. In the second question, we got movement on an inclined plane. Okay, so using the work-energy theorem on an inclined plane, the diagram below shows a crate of mass 500 kgs being pulled up a slope from point A to point B at constant velocity. Guys, the moment you see that word there, constant velocity, that's a key word. It's going to help us solve the puzzle. Slope makes an angle of 35 degrees with the horizontal. Frictional force is 2,500. So they're asking us to draw a free body diagram. So I would always want to draw a free body diagram showing the forces acting parallel to the slope, especially when I'm given the angle of inclination. So the first force I would put there is the FG parallel. The other force, the frictional force. And the other force that I would put there is the normal force. Then I'll have FG perpendicular, and the force that is pulling the object up, force F. Okay, now calculate the work done by frictional force. Well, work done by frictional force is 2.2.1. So the work done by frictional force will be the frictional force times distance times the cos of theta. I'm going to use the work formula. The frictional force is 2,500. The distance is 8. The distance is 8 times the cos of what? Well, we know that frictional force always acts at 180 degrees to the direction of motion, which is the 0 degree direction. So cos of 180. Multiplying this on a calculator, get negative 20,000 joules. So frictional force is negative 20,000 joules. Okay guys, work done by the gravitational force. We've spoken of 3 ways to calculate the work done by gravitational force. Look at the information given. We're given the angle of inclination and the length of the incline. So we can either use the component of gravity approach, or we can consider the force of gravity acting downwards, measure the angle. So I'm going to use the component of gravity approach. So first, let's work out what FG parallel is. FG parallel is mg sine theta. What is mg going to be? It's 500 times 9,8 times sine 35. This will give me 2,810,52 newtons. Now I can work out the work done by gravity. Gravitational force times 8 is going to be cos of 180 again. Why? Because the gravitational force, or the parallel of gravity along the inclined plane, always acts down the slope. So this gives me a negative 22,484,16 joules. This is a negative 22,484,16 joules. Okay. Now, in the last question, 2.3, they're asking us to use the work-energy theorem, and we call this kind of questions limited question. The question is limiting the approach that we can take to solve it. We're going to have to do that. To use the work-energy theorem, we're going to have to use the idea that W net is equal to delta EK. W net represents the total work done by the forces, or the work done by the net force. In this case, we can use the work approach because 2.2 asked us to calculate the work. So let's calculate the work done, the total work done. The total work done will be the work done by which forces? All the forces that are parallel to the direction of motion only. Force F, FG parallel FF. The other two, the perpendicular forces, do zero work. So, work done by friction, work done by gravity, work done by force F, the total of that is equal to the change in kinetic energy. But the object moves at a constant velocity, so that should be zero. Okay, so if I'm going to go to the bottom of the page on the right here, say work done by friction is negative 20,000 joules. Work done by gravitational force is negative 22,484,16, plus the work done by force F is 0. Take all these values across, they become positive, and add them. The work done by force F is going to be 42,484,16 joules. Okay, now that we got the work done by force F, we can easily calculate the magnitude of force F. We now know the work done by force F. We can calculate the magnitude of force F. So we're going to say force F times 8 times the cos of 0 is equal to 42,484.16. Cos of 0 is 1, so we divide both sides by 8. We get force F is 5,310,52 newtons. So in the last question, we've got a box of 100 kgs being pulled up by a force of 1,730 newtons through a height of 20 meters. Initial velocity is 0. Final velocity of the box is now 10 meters per second. We want to use the work-energy theorem to calculate the magnitude of the frictional force. Okay, so the free body diagram, we're going to have the force that is pulling up, the 1730 newtons, the forces opposing the up motion, gravitational force, and frictional force. Okay, we can see that the object's velocity changes from 0 to 10, so there is acceleration here, so there is a net force, right? The net work done will be a combination of the work done by the 1730 Newton force, the Fg, and the frictional force. So perhaps it might be worthwhile to calculate the work done by each of the forces and then use the Work-Energy Theorem. So we're going to use W net is equal to delta Ek. We can see the velocity values, so we can work out delta Ek. So let's work out the work done by gravity. Okay, so the work done by gravity, so we know that is the 0 direction. This will be the 180-degree direction. So gravity and frictional force are going to do negative work. Okay, so the work done by gravity, we can use the EP formula mgh. So we can say okay, times the cos of 180. So the mass is 100, 9,8, 20, cos of 180, negative 19,600 joules. Right? So when we enter into this formula, we're going to have a negative 19,600 joules. Let's leave the joules. So that is the work done by gravity. What will be the work done by the applied force F, the pulling force? It's going in the 0-degree direction, so it's times 20 times cos of 0. So the work done by the force that is pulling is actually 34,600. So we're going to add the 34,600 plus the work done by friction is now equal to the delta Ek. What is the delta Ek going to be? Well, delta Ek means final kinetic energy minus initial kinetic energy. Initial kinetic energy is 0. So the final kinetic energy will be a half times 100 times 10 squared, so 5,000 joules. Now we've got all the ingredients we need to calculate the work done by the frictional force, which becomes negative 10,000 joules. Okay, now to get what the frictional force is, we're going to divide by 20, because we know that work done is basically force times distance. So if we divide the negative 10,000 by 20, we get the work done by friction. So work done by friction is now F times 20 times cos 180 is equal to negative 10,000. Okay. So the negative, so we divide both sides by 20 cos 180. 20 cos 180 is the same as negative 20. So just divide both sides by negative 20. F is equal to, frictional force is now equal to 500 newtons. So we've looked at work done on a horizontal surface, inclined plane, and a vertical plane. Thanks guys for watching. We'll see you guys next time. We'll talk about the power ideas.